All right. So when we go to use these optimization problems, it's usually going to mean we're looking for the best price or amount, and we're trying to minimize or maximize the costs or profits. So the idea is, if I'm worried about things getting too expensive at the factory I'm working at, I'm going to try to minimize the costs because I might be able to make more items, but it might cost more. If I don't need to make that many items, then I'm not making the money that I need to be able to pay all the people that I've got working all these extra long hours. So that's the idea behind this. They have a big set of steps here. Like all word problems, you got to define the variables, you write your inequalities to go with it. Step three, we've already done that. That is graph the system of inequalities. Find the coordinates of the vertices of the feasible region. We already did that. The thing that we had before was the function was just given to us. This time it's different. We have to write the linear function that's going to be maximized or minimized. So the f of x, y thing that we keep talking about. And then we plug those coordinates in and we identify them just like we did on the last ones. Except now there's going to be some sort of context to the problem instead of just plugging it in. So for example 3, the optimization with linear programming, here's the scenario. An electronics company produces digital audio players and phones. A sign on the company bulletin board is shown. So you can see that's the little table that they have down there. If at least 2,000 items must be produced per shift, how many of each type should be made to minimize costs? The company is experiencing limitations or constraints on production caused by customer demand, shipping, and the productivity of their factory. Basically, if they make a billion phones and digital audio players, which I don't know if they even exist anymore, they can't ship them all out. They can't get them out fast enough. They would just get a bigger and bigger pile at the warehouse, and that's not good because you're making something that you're not selling. A system of inequalities can be used to represent these constraints. And then we got the keeping costs down. We can do it. Our goal, and it gives us some values here. So what we're going to do is we're going to try to define some variables. Well, we're building two different kinds of things, an audio device and a phone. Now you could use A and P for those, or you could just use X and Y. And now you've got your variables defined there. The next two columns in this table are the minimum and maximum. Whenever you see something like this about what's being produced, what you're getting here are actually horizontal lines. So they're saying for the audio device, which is X, you're going to make at least 600, but you're not going to make more than 1,500. For the Y or phones, you're going to make at least 800, but you're not going to make more than 1,700. If we make more than 1,500 and 1,700, it's no good. We're not going to be able to handle shipping all the stuff. And the last part actually comes from the scenario. If at least 2,000 items must be produced per shift, what are we going to do? So there, when you're combining it, you have audio and phones being combined together, you're not going to produce any more than 2,000, which means you want to produce less than 2,000. So now I've got my 3 inequalities. And they had it as a later step. I like to do it all in the beginning. The big thing here is I noticed there's another row called cost per unit. So I am going to use that to make a function for cost, f of x, y. The cost of producing audio devices is $55. So for every one of those you make, it's going to cost you $55. And for every phone you make, it's going to cost you $95. So there is our function. Now, I think I've got myself all the relationships. I've got my function. And let's go ahead and start graphing it. Now, an important thing here, we have very large numbers. So our graph is going to be large, but in this kind of scenario, it's all going to be in the first quadrant. So we're going to keep them all here in the first quadrant. One thing I'm going to do is I'm actually going to take all of these functions here and drag them down in the page so that we can see it while we're graphing. There we go. So now we can see the functions while we're graphing. So I think 20,000 is a good place to go for where we want. Let's see how many marks I've got set up on my graph here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll mark that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, look at that. Exactly 20. So that's 2,000. Half of that would be 1,000. So every mark is basically worth 100. Because if you have 10 100s, that's 1,000. So I'm going to be a kind of cheater pants here. 1, 2, 3, 4, 5. And I'm not going to mark every single line. 1, 2, 3, 4, 5. Because that is just going to take too much time. But with graph paper, I can easily count out all the lines in between. And let's do the same for the other side. 1, 2, 3, 4, 5. That's 500. 1, 2, 3, 4, 5. That is 1,000. 1, 2, 3, 4, 5. 1,500. 1, 2, 3, 4, 5. And 2,000. Let me see, I actually need a little bit of space there to the side. And I'll bring it down just a smidge so we can see below. So if you remember, for my two variables, X was the audio players. So I'm going to label my X-axis here, audio players. And for my Y-axis, it is the phones. So I'm going to label that phones. Okay. Now, we have a pair, like a compound inequality with the X values. So that's giving me my vertical lines for my audio players. And I'm actually going to draw it with the straight line tool. It's going to go straight up here. And we do that again at 1,500. So there we go. There is my bounded region for, or unbounded region for just the audio players. It has to be between those two lines. Now in green, I'll do the Y values. So that goes from 800. So we'll go up to 800, 6, 7, 800. There we go. And its maximum is 1,700, which is up here. And for the Y values, it has to be between those two lines. So right now, it looks like we've got this square in the middle is our feasible region. But we have one more equation we have to do. And this one's kind of important. I'll graph this one in blue. It is relating how many things that you're going to build during a day. So the maximum is 2,000. Well, forgive me. There must be a cat outside. The function, because it's just x plus y, I'll be right back in the video. We'll pick up right here where we're going to graph the line.